Page 8 of Polynomial Models bookwork. For this problem, you will need to remember that the volume of a rectangular prism, or kind of like a cube, is length times width times height. Okay. So the diagram represents a box with volume 16 cubic centimeters. The base of the box is square with sides x. The height of the box is y. Okay, it's kind of hard to see here, but so the height is y and the sides are x. Okay. Write an expression for the height y in terms of x. Let's see. Well, we do know that volume equals length times width times height. So we'll write volume equals length, which is x, times width, which we know is x, times height, which we know is y. And we also know that the volume is 16. Okay, so now if you figured it out, pause the video and solve for x. If you don't know, then continue on. So we have x times y equals 16. X squared times y equals 16. Now we want to write an expression for the height y in terms of x. In terms of x means that you're only going to have the variable x in the expression. So we want y on the left by itself. In order to do that, we need to divide both sides by x squared, right? 16 divided by x squared. Okay, so there's your expression, y in terms of x only. Okay, B, copy and complete the table below for the function y equals f of x from part A. Give your answers correct to two significant figures. So you're going to use this function to fill in the table. So you're going to put in values like x equals 0.5, x equals 1, x equals 2, 4, 8, 10, and we're going to see what we get out for x squared. There's a couple ways we could do that. We could just type in all the numbers, right? And we'll do one just like that. We'll do 16 divided by 0.5 squared. Okay, and that would give you 64. So that would be 64. Now the others, you could just use y equals. You could make a table, right? You could put 16 divided by x squared, and then you can get a whole bunch of values at the same time, right? So let's see. Got to go down to where it goes, become x equals 1, x equals 2. Okay, of course x equals 0 is an error because it's an asymptote, right? So 0.5 was 64, right? 1 is going to be 16. 2 is going to be 4. 4 is going to be 1. And I'm just getting these numbers here from the table. 8 is going to give me 0.25. And 10 is going to be 0.16. Okay. All right. Draw the graph of f for x equals 0, between 0 and 10. You notice it has u is less, or x is greater than 0, not x is greater than or equal to 0, because 0 is an asymptote, right? Use a scale of 1 centimeter to represent 1 centimeter on the horizontal axis, 1 centimeter to represent 10 units on the vertical axis. So 1 square on the horizontal axis is 1, 1 square on the vertical axis is 10. Okay, so let's use the graph paper here. And okay, so I would use a ruler, of course, if this was the test. And I'm going to put 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then on the y-axis, we're going to count by tens, remember? 40, 50, 60, 70. Okay, and then we'll go back and get our data. We can get some of it off the calculator here. Remember 10 is 0.16. Well, that's going to be really small because this is like, one of these squares is 10. 8 was 0.25. It's also going to be really small. It doesn't even show up here. Let's see, what else do we have? We had like 4 was 1 maybe. Yeah, 4 was 1. And 1 was 16. So 4 was 1, still barely shows up here. And 1 was 16. 1 is 16, it's up here. And 0.5, I don't remember what 0.5 was. I think it was 0.64, wasn't it? 0.5 was 64. So 0.5, which is here, is 0.64, or 64, so it's about there. Okay, now let's use the blue pen, and this is a hyperbola, or kind of a hyperbola. So it looks kind of like that, you know. Okay, and then it says, what happens to the height of the box as the values of x tend to infinity? So remember that as x goes to infinity, it's like going to the right, and you can see that it's getting very, very small. So we could say that it's getting very, very small. We could say it approaches 0. Okay? So that happens to y approaches 0, right? Because the height of the box is y. So as x gets to be a big number, y approaches 0. Okay, let's move on. To do number 8, 1 liter equals 1,000 milliliters. 1 milliliter equals 1 cubic centimeter. Just reviewing from a long time ago. So remember that milliliter means 1/1000, so you need 1,000 milliliters in a liter. And remember that 1 cubic centimeter, which is maybe about this big, of water is equal to a milliliter. So if you have a 10 centimeter by 10 centimeter by 10 centimeter cube, that is a liter. The diagram represents an open container with a capacity of 3 liters. The base of the container is a square with sides x. The height of the container is y. So this is a cube, just like, or not a cube, but like a rectangular prism, just like the one we saw. Sides are x by x, and the height is y. It's an open container. Write down the volume of the box in centimeters cubed. We're going to use the same equation we had before. Volume equals length times width times height. Length times width is x times x. Height is y. Find an expression for the height in terms of x. Same as the one above, right? So you're just gonna put what are we gonna put in for volume for this time? Write down the volume of the box in centimeters cubed. Because we know that the open container has a capacity of 3 liters. So 3 liters in centimeters cubed, let's do this conversion. So 1 liter is equal to, and remember how to do unit conversions, we put an expression which is equivalent to 1,000 milliliters on top, 1 liter on the bottom. We cancel out the liters. Then we multiply by another expression equivalent to 1 milliliter equals 1 cubic centimeter. Cross out the milliliters, and so we get 3 times 1,000 would be 3,000 cubic centimeters. So 3 liters is equal to 3,000 cubic centimeters, and let's see, that would be equal to x squared times y. We're going to take that and put it right there, right? And then it says find the expression in terms find an expression for y in terms of x. So we have to divide both sides by x squared. So we have 3,000 divided by x squared. That's the answer to B. Find an expression for the surface area of the container A in terms of x. Okay, the surface area of the container. The only trick to this is the top is open, so we don't count that. But basically, we're going to count the bottom surface area, which is a square that's x by x, right? So the surface area of this would be x squared, right? And then we have four pieces that are side pieces, and they are all the same. They have x width and they have y height. So the area of each of those is x times y. And there's four of those, okay? And that's confusing if I write times 4, right? I'm just going to put dot 4. And then the bottom, there's only one piece, so that would just be x squared. So we're going to add those two together to get the total area, which will be x squared plus 4xy. And now the only thing we need to do here left is it says we're supposed to find the area in terms of x, and we still have a y there. How do we get rid of that y? Well, we have an expression for y above there, right? So we have 4 times x times the expression for y, which is 3,000 divided by x squared. Which, so now we have x squared plus 4 times 3,000, we could just do that, right? 4 times 3,000 would be 12,000 divided by x, because we have x squared on bottom and we have x on top. Cancel those out. So now we have x squared plus 12,000 divided by x. Okay, and then we have the table below. Give your answers correct to two significant figures. This is similar to what we were doing above. We're just going to figure out the area for different values here. And again, we can use our calculator to do all the hard work here. We'll put in our formula, which is x squared plus 12,000 divided by x, and we should use parentheses here, because we know how dangerous it is not to. Okay, and then we will look at the table, and let's fill in some of these values here. 5, we can put in 2425. And it says the two significant figures, so 2425, we could just put 2400 because two significant figures, right? Let's see, what about for 10? 10 would be 1300. It's already two significant figures. 15 would be 1025. So 1025 in two significant figures would be 1,000. 20 would be 1,000. 25 would be 1,100. 30 would be 1,300. And 35 would be 1,600. Okay. Okay, draw the graph of A4. Okay, now we need to draw the graph on the graph paper. We're going to put 2 centimeters for 5 units on the horizontal and 1 centimeter for 400 units on the vertical. Okay, so every square is going to be 400 on the vertical. Every square is going to be 2.5 on the horizontal. 2.5 on the horizontal. Okay. So let's see. So every 2 is going to be 5 on the horizontal. And the vertical, every 1 is going to be 400. Okay. 15, 20, 25, 30. Remember, it goes up to 35, right? Okay. And now these values are really hard to remember. We're going to have to flip back and forth here. For 5, we have 2,400. So for 5, we have 2400. 5 would be 2400. And 10 would be 1300. 10 would be 1300. Whoops, 1300 would be much lower, right? 1300 would be down here. Okay. And 15 would be 1,000. 20 would be 1,000. 15 is 1,000. 20 is 1,000. 25 would be 1,100. 25 would be 1,100. 30 would be 1,300. And 35 would be 1,600. 1,600. Okay. Let's try to connect these in a curve. Okay. So that's the graph. Use your graph to decide if there is a value of x that makes the surface area of the container a minimum. If there is, write down this value of x. Okay, so actually this graph we made, and I should have written it here. I should have labeled this vertical axis A because it's the area, and this would be x, which is the, the length or whatever. Okay, so is there a value of area that is minimum in this graph? And I would say yeah. I would say it's somewhere around there, without knowing exactly. And let's see, did they ask us to find it then? If there is, write down this value of x. Okay, now it doesn't really say if we're supposed to use the graph to do that. It says to use the graph to decide if there is a value. Yes, there is. Now, I think it'd be okay to use the calculator to figure this out because it never says not to use the calculator. So we could graph it, and we should see a graph just like we drew there, except that I think we're zoomed out, or we're zoomed in too close. So first we'll do zoom standard, and then we'll do window, and we need to open it up quite a bit. Okay, so we'll put like big numbers in here for x max. We'll put, I think like 1,000. Oh, it doesn't need to be 1,000. It could be 100, right? And then for y max, I'm going to put something big like 1,000. Actually, we need to put something bigger like 3,000. And now I think we can see it. Okay, so now we see something like we did. Now let's find out what the minimum point is, because that's what they wanted to know. We could use table, we could use the graph, we could see it's around 1,000, but since we have the calculator, why don't we get like a really accurate value? So we need to move the cursor to the left side of the minimum point. Enter. I go to the right side of the minimum point. Enter. And so it says that the point would be, and then we need to say guess, yes. Okay, so the minimum point would be x equals 18.1 and y equals 990.57, so we could say 991. We'll just leave 3 significant figures because that's normally what you do for IB. Now, do we want x or y? Well, they say, is there a value of x? And if there is, write down this value of x. So all we need is x. We don't need the y in this case. Okay? And that's it for this section.